Okay. As I said, okay. So we're going to deal with how light interacts with matter. There are three ways that light interacts with matter. The first is that light reflects off of it, so the light wave hits the matter or the object and it just bounces off. The second way is light can travel into the material, and if it travels into the material, then it can, if the material is transparent, then it can get bent and move through the material, and that's known as refraction. And then the other possibility is absorption. We're not going to really talk about that. But what we're specifically going to talk about is refraction. So this is the refraction of light. Okay. So actually, let me show the. Oh, and can you see? You know what? I completely forgot.
Yes, sir.
To share my screen, so you probably have no idea what I'm doing. Okay. And I don't want to do that. I do want to do this. Okay, so if I say this is basically like a little simulation of a laser pointer, okay, is if I turn this on, okay, you can see these rays basically come in, the light waves come in, they hit the surface, and then they're compressed. The distance between each of the dark spaces, which is basically the bottom of the light wave, gets closer together. And because of this, the light slows down. Actually, you can even see they've done a good job here. You can see that in here, it's moving at a relatively quick pace. Here, it's moving much more slowly, okay? So this effect that the material has on the speed of light is related to something called the index of refraction. So the index of refraction, okay, it's typically represented by a small letter n, and this is equal to, let's say light speed in vacuum over, say, light speed in some material. Okay, so this would be C over V, okay, where C is the speed of light in vacuum, which is, it's like 2.99 something something. I'm just going to write it as 3.0 times 10 to the 8th meters per second, okay? For most ordinary materials, the speed of light inside the material is less than the speed of light in vacuum. So V is usually less than C. There are some exotic materials where the phase velocity, and that's what this is actually related to, is larger than the speed of light. But those are like plasmas and various complicated crystals and God knows what else. We are not going to be doing anything with those. So we expect that V is going to be less than C. Okay, so let me actually want to bring up that. Try again. That. Okay. Oh, okay. Do you see anything now? Can you see my notes now? Sorry, I should have had the thing up. Maximizing it. Okay, how about we do this? I want to be able to see the comments. So is that, okay, good, okay. Okay, so V is usually less than C. So what this means is that if I look at C divided by V, C divided by B would be less, or excuse me, C divided B would be bigger than 1. Okay. So, and this is an important criteria, particularly for the experiment that we're going to be doing today. If you get an index of refraction, well, let me step back. So what this tells us is that the index of refraction should be bigger than 1. It would be equal to 1 if you were moving in vacuum. But if you have an index of refraction that's less than 1, that means that you've either invented warp drive, and you're going to win a Nobel Prize and be a billionaire, or you've made a mistake in your calculation. And it's more likely to be the second than it is to be the first. And this is a big indication if you've made a mistake in the calculation, is if you end up with an index of refraction that's less than 1. A lot of times when I'm checking students' work, when they're doing this experiment actually in the lab, the students will, go along, they'll do their calculations, and they'll bring them up for me to approve them, and I'll point out that their index of refraction is less than 1. They've done all these beautiful calculations and plotted all these graphs, and they got to the bottom, and they didn't realize that they had calculated something wrong. So please take note. If you get an index of refraction that's less than 1, you've done something wrong. You keep that in mind, it'll save you a lot of headache later on when you're doing various calculations. Okay, so if I have, say, an interface between two materials, so this is, say, an incident material, and this is the material that the light ray is traveling into. So we have a light ray coming in like this. Okay, there. Okay, it hits the surface, and then if these two were equal to each other, it would continue just basically going straight in. Okay, so this would be the line if Ni was equal to Nr. Okay, but what happens is the light ray gets bent to, well, it can do one of two things. It can get bent to a smaller angle, like this, or it can get bent to a larger angle, like this. Okay, the green one is the case, and this is the one we're going to take up today, when N incident is less than Nr. So we're going into an optically thicker material, a material that it's harder for the light to travel through. The other case, which we're going to take up next week, is when Ni is bigger than Nr. Okay, now what we're specifically going to be looking at are angles. We want to measure angles and how the angles change as we go from one material to the other material. So to do that, I need to have some way of measuring the angle. The way that's typically done in optics is you look at the angle compared to the line that's perpendicular to the surface. So this line that's perpendicular to the surface is known as the normal. Okay, and we are looking at this angle in here. This is theta incident, and I want to compare it to this angle in here, which I'm going to say is theta r for theta refracted. Okay, and the equation that relates all of these is known as Snell's law. Okay, and what Snell's law says is N incident sine theta incident is N refracted sine theta refracted. Okay, so this is what we're specifically going to be looking at. Okay, for what we're doing today, we're going to be starting out in air. So N incident is N of air, and the N of the index of refraction of air is like 1.00 blah 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 blah. Okay, it's very, very close to being 1, which is what well, it's very, very close to being 1. So we really don't have to worry about it if we're dealing with light traveling just through like 10 or 20 or 30 or even a meter. Okay, you're just not going to really see the effect of the light ray being bent by the interaction with the air. If light is traveling through the Earth's atmosphere, say you have sunlight traveling through the atmosphere to get to your little eyes on the ground, then this can start to have a pretty big effect on the sunlight. Okay, so, but for us, we're not going to have to worry about that. So our Ni is 1. So I can say that this is equal to 1. So I can write sine theta I is nr sine theta r, or I can solve this for nr and get sine theta I over sine theta r. Okay, and this is basically the equation that we're going to be working with. I'll give you all a minute to catch up. I tend to go fast, I know. So when you're ready to go on, just say ready. Okay, Jenna says she's ready. Leighton says he's ready. I get a couple more. Alejandro says he's ready. And Yvette says, is it, and now, okay, Yvette, I'm not sure if you're a guy or a girl. I'm sorry for that. The genders, it's really hard with names these days to tell what the gender is. So if you want to tell me what your gender is, I would appreciate that. And Ella says she's ready, and Arturo, girl. Okay, I will try to remember that, Yvette. If I don't, please forgive me. And please remind me. I'm very dumb about these things. Okay, so the other thing I want to do with this is I'm going to solve this for sine theta r. Okay, and that would be equal to, well, I just bring the nr over, so this would be 1 over nr sine theta I. Okay, and the reason I'm doing this is if I plot this on the y-axis and I plot this on the x-axis, then the slope is this thing here. Okay, would be 1 over nr. And then the y-intercept would be, well, theoretically it should be 0. Now you'll probably get a number, but it should be small. Hopefully less than 1. Hopefully very much less than 1. Okay, so we should expect something that's a small number. And then the slope should be 1 over the index of refraction. Okay, so when you're looking at, there's a question specifically in the questions that asks you to plot out, to put down what the various pieces of the best fit equation are, and also to compare your the slope to what it should be theoretically, and it should be equal to 1 over nr. Okay, so can I go on? Is everybody good so far? What is after the y here or here? The plus y. Oh, intercept, int. Yeah, this is y-intercept. That's what that is. Does that help? Okay. Okay, Alejandro says he's ready. Deacon says he's ready. Devin says he's ready. I get one more. Bonnie says she's ready. Okay. All right. So now that we have kind of a basic understanding of the theory that we're looking at, what I want to do is actually look at the simulation. And the nice thing about this simulation, it's pretty close to what we'd actually do in the lab. So this one's actually pretty good. The first thing I'm going to do, actually the first thing I'm going to do is shorten this a bit so I can see the chat. And, oh, not just yet. Okay. Now, I'm trying an experiment here. The lights just went off. I have a Nerf gun. I'm going to see if I shoot at the thing, if it'll turn it back on. No. Ow. I didn't actually hit the little sensor. I wonder if I hit the sensor, if it would turn on. Maybe I could just knock it off the ceiling. Anyway. Okay, moving on. So I have, here's my light ray, basically. It's like, you can think this is like a laser pointer. The laser's coming in, it hits the surface here, and then part of the ray is being reflected out. That's what we see here. And this is the part of the ray that's basically moving inside the material. And the material in this case is water. And the index of refraction of water is well known. It's 1.33. Okay, so we have a theoretical value that we can compare our experimental values to. So, so I'm going to take my protractor here. I'm going to set it so that kind of the bar across here is on the interface, and the little mark here basically is right up on that normal. Okay, and the little dotted line that you see there, that's the normal. Okay, so we see that. Okay, so the idea is I can adjust this, and by adjusting this, I can adjust this angle in here, that's the incident angle that I can measure with the protractor, and then on the other side, I can measure this angle in here, which would be the refracted angle. Okay, so in terms of the data table for this, so if I go over to Canvas, okay, so this is what you should see when you go over to Canvas. There's the data table. Okay, and I'm going to go ahead, oh, actually I should have done, I should fix that. Okay, and I'm going to go ahead and make this larger. See what this does. Okay, so here's the data table. So you have your incident, your angles, so from 20 to 70. So what I'm wanting you to do is basically using this as a template. I want you to put this into Excel or LibreOffice or OpenOffice, whatever, and then use the spreadsheet to basically do all of the calculations for you. And then once you've done the calculations, you'll copy those results and put them into a document and then submit that as a PDF, more or less like we did last week. The simulation website is also up here if you need to find it. It's also here, the refraction simulation. This is also a link to the actual simulation as well. Okay, so based on this, actually, yeah, this is the data table. Okay, I'm going to open up Excel. Yes. Oh, oops. Okay, do that. Okay, and okay, so I want to put these here. Right now I'm writing out like theta I and theta R. Later on, I'll show you how to actually change it so it puts in a Greek letter theta. But that's something I don't want to worry about too much today. So, okay, so let's say B4. So this is theta. If you know how to do the theta I and theta R, please feel free to. First, if you know Excel well enough that you don't need to listen to me drone on and on, please feel free to just start the experiment. It won't hurt my feelings. Okay. Now, one of the problems with Excel or most spreadsheet programs is that when you calculate the sine of an angle, they assume that that angle is in radians. So we need to convert each of these from degrees to radians. So that's what I'm going to do in the next two columns. Is theta I in radians and theta. Okay. And then once I have those two, okay, now I'm going to do the sine. So I'm going to do sine theta I. Theta R. Okay, and the signs do not have units associated with them. So I guess I should really be consistent with what I did in fall or the spring, is do that to indicate that they don't have a unit. Okay, and then finally I have here, I'm going to have my NR value, which is also does not have a unit associated with it. Okay, and then over here, I'm going to start at, say, 20, 25, oops, oh, 5, 30, 35, 40, 45, 50, 60, 65, 70. I think 70 was my last one. Yes, okay. And that is a lot of data, but the truth is that because the spreadsheet is going to do all the calculations for you, it's not actually going to be that bad. You're really only going to be filling in the equations in the top and then letting the spreadsheet calculate all of the rest. So that's one of the reasons why I gave a bunch of data points. And it's not too terribly hard from the simulation to get the data. Okay, and that's the next, well, okay, before we go any further, okay, I'm going to give you all a minute to catch up. So if you haven't put this stuff in your spreadsheet, you might want to go ahead and do that now. Now would be a good time. If you are ready to go, let me know by putting ready in the comments in the chat, or if you just say ready with your mic unmuted. Alejandro says he's ready. He's on top of the game. Jenna says she's ready. Arturo says he's ready. Melanie says she's ready. Okay, I think that's okay. Good. Wow, I just realized you can zoom in on Teams. Oh, wow, I didn't know that either. That's interesting. I'll have to try to look into that. Good to know. Thanks for sharing. Okay. All right. So the first thing I want to do is figure out what each of these refracted angles is. To do that, I want to go to my simulation. Oops. Yeah, go to my simulation. And I want to start at 20 degrees. Okay. On this, each of the large marks is 10 degrees, and each of the smaller ones is 5. So 20 degrees would be that. Okay. And you'll notice the reflected ray is about 20 degrees as well. That's what you can expect. You can drag it around as an individual can drag it around. Okay, so I have my incident angle is 20, and then my refracted angle here is, that's going to be about 10. Then the next one, the little one over there, is 15. So that suggests that the refracted angle there is 15. So I'm going to go over to my spreadsheet and put in 15. Okay, then I'm going to go back here, and now I want to set this to 25. Okay, and at 25, it's just a hair under the 20 degree mark. So I'm going to say that that's 19 degrees. Okay, and that is kind of one of the problems with this simulation is we can't get super into the little degradations, but that's okay. Okay, and if I do 30, okay, that's going to be like, that's 20, it's between 20 and 25. Looks like it's halfway between the two, so it's going to be 22.5. Okay, so everybody's numbers for this will probably be a little different. It depends on how well you line up your protractor, you know, how well you can interpolate the various values here. Just do the best you can with it. There's going to be a little bit of error that gets introduced in there, but that's actually, from my point of view, a good thing. It keeps everybody from getting exactly the same numbers, which is bad if it's an experiment, okay, or at least an experiment for like what we're doing. Okay, so so hopefully everybody has a good sense of how, I'll do one more. I want to do one more. So let's do 35. So there's 35. And that looks like it's 20, 25, let's say it's 26. So let's say this is 26 degrees, okay? I'll let you fill in the rest of these, okay? So what I want to do now is I'm going to go through and put in the equations in the top row here, and then kind of go from there. So the first one, okay, if I want to go from degrees to radians, so I want to go radians is equal to, you want the value in degrees times pi, and for this, if you put in pi and then open parenthesis, close parenthesis, Excel knows, or OpenOffice or any spreadsheet will recognize that as being the 3.1415927 blah 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 blah. Okay, the pi that we all know and love. And then I divide this by 180. Okay, so that's the formula that I'm going to use to convert from degrees to radians. So if I go up here and do equals, and I want to click on this 20 degrees, and then times pi, open parenthesis, close parenthesis, divided by 180, I hit enter. Okay, and that's converted that to radians. And I'll drag this down. Okay. For this one, I want to do the same thing, except I want to put in the 15 degrees rather than the 20. So this is going to be equals that one times pi, open parenthesis, close parenthesis, divided by that one. I'll just copy this down. Okay. Give you all a minute to catch up, and then we'll go from there. Let me know when you're ready. Okay, Alejandro said he's ready. Ella says she's ready. Excuse me. Yes, Slayton asks, is the underlying subscript? It is. That's the, yes, that's the symbol that we use when we can't do subscripts to represent subscripts. Thank you for asking. That's a good question. Okay, so it looks like we have 4, so we'll go on. Okay, so now I'm going to do sine, and this is just, I want to do equals sine, open parenthesis, and since this is theta I want to click on that one, and then close, hit enter. Okay, that's calculated the sine of that angle. And I'll drag this down, go over here, equals sine to theta r, this one, close parenthesis, that. I take this and copy it down. Okay, and then remember, n r was equal to sine of theta I divided by sine of theta. Sure. I want to do equals sine of theta I divided by sine of theta r. Enter. I'm going to copy this down. Okay, and it gives me my other values. Okay, let me know when you're ready. And if you need me to go over something else, let me know. I think the first few lab periods that we're going to be doing, we'll be going a full hour rather than the half hour that I originally thought. And it's just to make sure everybody kind of gets the handle on spreadsheets. How do you do theta I, sine theta again? You do, okay, so let's go to this one. Let's just get rid of these. Okay, so here I do equals. I just type sine, S-I-N, or sin, parenthesis, and then you put in, this is sine of theta I, so I want to click on the theta I right here, and then close parenthesis, enter. I'll take this, copy it down, and here I do equals sine theta R, close parenthesis. Here, theta here is lowercase, okay. Oops. So if anybody wants to copy and paste, please feel free to do so. And I'll show you again, I'll show you how to do that next week. I'll show you how to do subscripts and superscripts too. It's not hard. It's just, I don't want to burden you with too much information all at once. Okay. Are you good, Devin? Did I get it? Did you get it? You can edit. Yeah. Yeah, you can do, yeah. Yeah, you're on top of the game there, Slayton. I just don't want to overload everybody. Slayton, if you know how to use this, please feel free to just ignore my little song and dance here. That's what this primarily is for, is just for the people who don't know how to use. Arturo says thank you, though. And with the spreadsheets, everybody knows a little something different about them. So we all learn, I always learn something new every time I use one practically. Okay, good. Well, I appreciate that. We all appreciate that. Thank you, Slayton. It's good to share the knowledge. Okay, while y'all are catching up, I'm going to go ahead and fill in, I'm just going to fill in some random numbers for the rest of this column, just so I can use it to do something else. So these are just random numbers, okay? Don't worry about it. That's okay. Okay, so again, those are just random numbers I picked. Okay, Ella says she's ready. Okay, Alejandro says he's ready. Melanie says she's ready, and Jenna says she's ready. Okay, so that's 4. So, okay, so like I said, I went ahead and filled these in. What I want to do next is show you how to do kind of the standard statistical calculations that we've been doing. So the first thing I want to do is I want to take an average of these. So you could just go, equals, parenthesis, and then that, plus that, plus that, plus that, and do, divided by however many data points. That would be one way to do it. But Excel actually has an average function. So if you type average, open parenthesis, and I click on the first cell with the first value, you hold the shift key down and you click on the last value and then close parenthesis, enter. Okay. and that calculates the average value. So this would be NR average. Okay. Let me go through that again. So I'm going to do equals and spell out average. That one, hold the shift key down and then click on the last value, close parenthesis, enter. Okay, and that calculated the average value. Okay, let me know when you're ready. Okay, Alejandro's ready, Slayton's ready. Jenna's ready. Oh, my lights just went. I have one more of these darts I can try. Oh, that one went off really badly. So much for that. Okay, Ella says she's ready. Okay, so the next thing I need to do is calculate the standard deviation. I'm trying to do subscripts, highlight. Yeah, there you go. Okay, so I want to do standard deviation. So that's that we could be using the term the SX, and this is of my NR values. Okay, so that's what I'm going to do. And here I'm going to do equals, and then if you're using Excel or LibreOffice, you should be able to do STDEV, and you'll notice it gives you all of these different choices. Okay, the one that we want is the .S, which is for the sample. So .S, open parenthesis, click on the first, hold down shift, click on the last, close parenthesis, enter. And that calculates the standard deviation. If you're using, is anybody out there using OpenOffice rather than LibreOffice or Excel? Okay, not seeing anything, so that's good, because OpenOffice is weird for some reason. Okay. All right, let me know when you're ready. Okay, Alejandro's ready. Devin's ready. Arturo's ready. So I'm gonna get one more. And Ella's ready. Okay. All right. So the next thing I want to do is I want to calculate the uncertainty. Okay. Remember the uncertainty. Let me do. Okay. Let me do this. So the uncertainty in my NR. I'm going to say this is DNR. Okay. Where my D is my delta. Until we figure out how to use a little a little delta. Again, it's not hard. I just don't want to go in there just yet. Remember, this is equal to, it's the standard deviation, or it's, yeah, it was the standard deviation. So this is going to be the SX of NR divided by the square root, so SQRT, of the number of data points, which in this case was 11. close parenthesis, enter. Okay, that's the equation that we're using. Let me check something real quick. Yep, it is 11. Okay. So over here, I want to do dnr equals the standard deviation, which is what I got up there, divided by square root of 11. That's the standard deviation. Or that's the uncertainty. Okay. If you need me to go over that again, let me know. Otherwise, if you're ready to go on, we'll go on. Let me know when you're ready to go on. Ella's ready. Alejandro, I'm disappointed. She beat you to the punch. Jenna's ready. Alejandro's ready now. Coming up on third. Like I'm calling a horse race. Slayton says he's ready. Okay, so we have two more that we want to do. One of them is we want to do our percent differences and our percent uncertainties. And if you remember, the percent uncertainties and the percent differences are how we quantify our accuracy and our precision and how well our data agrees with the theory. And on the data table here, yeah, if you go to the back page, I went ahead and put this in here as well. And these are these equations that I'm using. Okay, so the idea is that basically if it's less than 5%, it's very precise, very accurate, strong support, strong evidence that it's constant, if you're looking at it as constant, or accuracy or precision. If our percentages are between 5 and 10, then we drop the very or the strong, and it's just the value is precise or is accurate or is a constant or just supports theory. If it's between 11 and 20, we say that it is somewhat accurate or somewhat precisely known. It weakly supports the theory, and that the variable may be constant. So it supports the idea that it might be. And if it's bigger than 20%, then we'll say that our experiment, in our experiment, the variable is not constant. The experiment doesn't support the theory. Experimental value is imprecise, and the experimental value is inaccurate. Okay, so we want to remember these percentages when I'm asking questions about, like, can you say anything about the accuracy of your experiment? You do that by looking at these percentages and using that to draw your conclusion. Okay, so I'm going to do percent difference first because it's actually a little easier. So percent difference, actually let me give you the formula first. Down here, the formula was the percent difference is equal to 100 times our theory value minus the experimental value divided by the theory value. Okay, like that. So over here, I'm going to do percent difference equals 100 times the theory value. For this one, we're working with water. So the index of refraction of water is known to be 1.33. So that's our theoretical value. I want to do minus, I want to compare it to the average experimental value, which was this cell here. Close parenthesis, and then divide by 1.33. Okay, I got a 1% difference, which is pretty good. Okay. Let me know if you need me to go over that again, or if you're ready to go. Okay, Alejandro, that's coming in first. Devin's coming in second. Clayton's third. And Jenna's coming up fourth. Okay, all right. So, okay. So the next, oh, before I leave this, okay, remember percent difference? Percent difference is what we use to compare to theory. And when we're comparing to theory, we're talking about accuracy. So, in the question that asks you, are your values accurate? Or can you say anything about the accuracy of your variables? What it's asking is, can you calculate a percent difference? If you don't have a theory value to compare to, then you can't say anything about the accuracy. You're not saying that it's inaccurate. You're not saying it's inaccurate or accurate. You're saying that you don't know because you don't have something to compare it to. So that's what you want to look at when it's asking about accuracy. Also, if it's asking, does the experiment support the theory, you want to look at percent difference to tell if that's the case. Okay. And then the other one that we look at is percent variation. I'll put the equation over here. Okay. And this was 100 times our uncertainty, our DNR, capital DNR, divided by our average value. So it's going to do percent variation equals 100 times our uncertainty divided by the average value. Enter. And I got a 0.44. So it's pretty good. Okay. Let me know if you need me to go over that again, or if you're ready to go, or when you're ready to go. Devin says he's ready. Ooh, catching up on us. Jenna, ooh, Alejandro, where are you? Alejandro, oh my gosh, Alejandro, where are you? I'm so disappointed. Okay, for some percent variation, sorry, I have to do something. Percent variation, we're looking at variation in your values. Experiment. Okay. This is also looks at precision. Okay. So if your percent variation is low, like this one is, you can say that you know the index of refraction precisely. If the index of refraction is, or if the percent variation is high, then it's imprecise. The other thing I need to point out too while I'm thinking about it, this one also, let's see, back to this. This is the question is it a constant? Okay. If the percent variation is low, then that supports the idea that our experimental value is a constant. If the percent variation is high, that suggests that the experimental value is not a constant. And then depending on what the theory says, that either helps us or it hurts us. Here we expect the index of refraction should be a constant. It should be a property of a material. If you know what it's made of and how the atoms inside it are spaced, and you have a really good physical chemist that you know, they should be able to either calculate or put it on a computer and figure out what the index of refraction should be based on that information. Okay. Okay, just a few more things here. First thing I want to do is, this is the data, or at least part of the data for water. So I'm going to rename this sheet water. So I'm going to go over here to the sheet. I'm going to do a right click and click on rename, and I'm going to name it water. Okay, because that's our analysis for water. Okay. Now, if you look at the data table, okay, so there's the stuff for water and the graph. I'll talk about the graph in just a minute. And then there's this unknown case. So if we go back to the simulation, okay, over here, if you look at material, you have mystery A and mystery B. Okay, so what I want you to do with this is if your first name has an even number, make sure I'm consistent with, yeah. If your first name has an even number of letters, I want you to use unknown, or mystery A, I should say mystery, not unknown. If your first name has an odd number of letters, I want you to use mystery B. Okay, mine, yes, is odd, so I'm going to use unknown B. So I go over here, and we'll switch this over to mystery B. Okay, and then we're basically doing the same experiment. Okay, now, since we're doing the same experiment, I'm going to create another spreadsheet. So I'm going to click on the little plus here. That creates a new spreadsheet, and I'm going to call this one mystery. Okay, now here's one of the cool things we can do with spreadsheets. Okay, I'm going to click on this, and then I'm going to click hold, and I'm going to copy or select all of this. Actually, select just that. And I want to do copy. Okay, and this is, the first one is here is D4. So if I go over here, I go to D4, and I go paste. Okay, what I did basically is it's now pasted in all of those formulas. Okay, so these are all the same, so I don't have to re-enter that. These will probably change, so I'm going to just go through and delete those. So, okay, you'll notice all of these numbers did weird things. Actually, those didn't go away. Oh, because those would be the same. Okay. So if I go to the simulation, so for example, if I start at 20, okay, 20, that would be 15. So I'll put in 15 here. Okay, and now notice it filled out the entire column, or the entire row. Okay, if I go back here now, do 25, and that's going to be, that's 15, that would be 20, and I'm going to say it's 18. So that's 18, okay, and it filled in this one. Do just a couple more. 30, that's going to be, I'm going to say that's 21. And 35, that's, was it 10, 25. Okay, so what this means, I don't have to go back and redo all of these calculations. I just change these numbers, and the spreadsheet automatically recalculates everything. This is one of the reasons why we made spreadsheets. Accountants love, love, love spreadsheets because they could just make a small change in one number and it recalculates everything. They don't have to go back and get out their calculators and redo everything. We also, as scientists and engineers, love, love, love spreadsheets because they keep us from having to do a lot of calculations. So I think when I first started having the students using spreadsheets, they always complained, you know, can we just use a calculator, please? You know, by the end of the semester, they understand that, oh, this is really nice. This means I don't have to, like, you know, do a lot of calculations. But at the beginning, it's hard. And that's just because you're learning it. It's hard for everybody at the beginning. But you play with it a little bit, you'll get better at it, I promise. Okay, the first few steps are going to be slow, but we're going to get faster as we go. Okay, before I forget, I'm wanting you to do some graphs. So I'm wanting you to graph sine theta I on the x-axis, sine theta r on the y-axis. So if I go over here, my sine theta I, this is the x values, sine theta r are my y values. Okay, so we can do that. And let me do one other thing before I forget. So the idea is you highlight these, and then you do insert chart, or yeah, insert chart, and then it'll basically create a graph for those. And then you want to copy and paste that graph into a Word document like we did last week, and then you convert that Word document into a PDF file and submit it. So you're doing the same thing that you did last week, only with this data rather than with the other, and the data that you take using the simulation rather than data that I give you. And I put in here, these are the things that I'm going to be looking for in the graphs, just so that everybody's on the same page. Trying to think what else. Oh, there is one other thing I want to show you. You can see in here that you have a whole bunch of a whole bunch of decimal places in here. And in fact, if I copy this, I'm just gonna, oops, actually I want to do, I'm gonna get rid of this one. I want to put it in a Word document. And actually remember we want to do a couple spaces, and then we want to do paste. No, not that paste. Another paste. Okay. Sometimes this one's not so bad, but like in LibreOffice, I know that it will give you an enormous number of data points that makes it hard to actually fit everything on a single page. So what I want to show you real quick is how do you tell it to restrict the number of decimal points in the calculation, or the number of decimal points that displayed. Okay, so the way to do this is actually if I highlight the column, okay, and then I do a right click, and I want format cells, okay, and it'll bring up this interface. And you click on number, and it says decimal places. And I'm going to set decimal places to 4. Okay, so we don't really know it better than that. Okay, that's now restricted everything to 4 decimal places. Okay, I think I can go ahead and do that with all of these. Okay, like that. Okay, and the other thing I'm going to do is I'm going to highlight all of this. If you go up here, there's a little series of lines. This is going to center the numbers, so it makes it a little bit neater. And then for these, I actually like to have these right up against the number. It's just my personal preference. So that there as well. Okay. So then if I copy this over, okay, maybe a little bit nicer. Okay, you can also, remember, you can adjust the width of these. So like here, it's kind of going off of the edge. Here it was going off the edge. Going off the edge here. Probably need to press these a few little more. Okay, anyway, I think you get the idea. I don't want to belabor this too much with me being nitpicky. Okay, so does anybody have any questions? Anything anybody wants me to go over again? Oh, before I forget, okay, so we've got data tables, graphs, and then there's the questions here. I just don't forget about the questions. This is like the stuff that we did at the beginning of the spring semester. So you're looking at your percent variations and your percent differences to say things about accuracy and precision. I'm wanting you to use this template here, basically to write out your best fit line. Okay, I've given you that equation. I gave you that at the beginning, so hopefully everybody can do that. If you have trouble with it, let me know. I'm glad to help. I'd rather you ask than not ask. I think that's all I have. Does anybody have anything they want to ask about? I thank you, Bonnie. I try. And I know it's slow, but we will get better at this over time. I can guarantee it. Okay, seems like everybody's happy. So I'm going to sign off. I will be in my office until 7. If you run into trouble, please feel free to either request a Teams meeting, or you can send me an email on or a message to Canvas if you have questions about how to do this. And I would be more than happy to help. You're welcome, Jenna. So I'm going to hang up, and I will see you guys, I guess, tomorrow. Okay. So I'm going to, okay. Thank you, Slayton.